Hello everyone, I myself Siri Prodhituri from 3rd EC and the topic I chose was Newton's iterative optimization. In this optimization, we can find the root and minima of the given function in both single variable case and multivariable case. Firstly, for finding the root, the process is, as it's an iterative optimization, for every iteration we get closer to the root. This starts with an initial guess for the root, and then for every iteration the guess until the desired level of accuracy is achieved, we improve the guess. The formula for the Newton's method is xn plus 1 is equal to xn minus f of xn by its derivative, where xn represents the nth guess for the root and xn plus 1 is the nth plus 1 guess to be found from the nth guess. F of xn is its functional value and f dash is its derivative, and this Newton's method is derived from, as said, that the key calculation in each step of Newton's method is to find the tangent line to f of x at the point x1 and y1 and where it intersects the x-axis. Now initially let's find the x-intercept. The tangent to the line x1 and y1 intersects the x-axis at x2. As we know, the basic line equation is y is equals to slope into x minus the x naught plus y naught, and here the slope is nothing but the gradient of the function at the point x1 and it passes through the point x1 comma y1. So the equation can be written as y is equals to f dash of x1 into x minus x1 plus y1. As setting y is equals to 0, because we are finding the root, the functional value is 0, we get x is equals to x1 minus y1 by f dash of x1. y1 is nothing but its functional value at the point x1. Here finally we got that x2 is equals to x1 minus f of x1 by f dash of x1, and its algorithm to find the Newton's method is initially guessing the minimum for the x1, computing its derivative at the guess, then estimating the next guess and finding its functional value. And if the x is close to the true minimum, then stop. Otherwise, by using the Newton's formula, repeat the steps. And its geometrical interpretation. Newton's method for solving equations is based on its geometry of a curve using the tangent lines to the curve. It requires calculus in particular differentiation. Roughly, the Newton's ideas follows as: in the first figure, we seek a solution to f of x is equals to 0. This is the point we need to find. A tangent at a line x1 is a x1 y1 is a good linear approximation to f of x near x1. So our next guess x2 is the point where the tangent line meets the x-axis as shown. From the Newton's method, we get the value of y2 and calculate y2 and again its tangent. If it's 0, if its functional value is 0, we are finished. If not, we draw the tangent line to f of x at x2 y2 and next guess x3, the point where the tangent line intersects the x-axis, and this process continues till the desired value of our function is achieved. Then the Python code for the above discussed method is importing SymPy library for finding derivative and x as a symbol, and matplotlib to plot the graph of the given function. Initially declare x is equal as symbols in the function of x. As f I chose was the function x square plus 2x minus 2. With the help of the SymPy function, df is declared as a differentiation of the given function in variable x. Then input of initial guess and number of correct decimal places is chosen. Initially I is equal to 1 while the condition is true, the guess was converted into a string for string slicing. Here a is found from substituting the value of initial guess in the function, and b is the derivative of the given function at a particular z value. By using Newton's formula, xn plus 1 is equals to xn minus f of x by f dash of x. Here this formula represents that y is equals to z minus a by b. Y is the next iterative guess in every iteration. As z is a guess for the previous iteration and checking its both values, if they are equal, the condition is false and it terminates from the loop, or else if they are not equal, the condition becomes true and it runs the loop till they are equal. And then plotting the graph. Xp is the point that we choose on x-axis and yp is the point that we choose on y-axis. The range I took was from z plus 2 to z plus 3, and appending these values into xp and its corresponding values from the f dot substitute x comma y to yp, then plotting a graph between xp and yp with a label graph. It gives the functional graph of the given function. For the function I choose, the results are for x square, this function, the initial guess I given was 1 and the correct places of decimal where we need to check was 3. For every iteration, these are the values I obtained, and for the graph, x points and y points are correspondingly shown here. For these points, the graph I obtained was a curve. At the point x 0, 0, this is the root of a equation and we can get it from the code. And the other way to find the root, if the number of iterations in a Newton method are given. The same code is similar to the previous one. The only one here I changed was n is declared as a number of iterations. Here I took the for loop in the range of n. For every loop, the value of I decreases. By substituting in the same formula, xn plus 1 is equals to xn minus f of x n by f dash of xn, we get the next guess. As the number of iterations come closer to 0, it terminates here and then it prints its functional value here. For plotting the graph, it appends the points into xp list and yp list as arrays and then plots the graph between these both points. For the same expression, the initial guess was 1 and the number of iterations I chose was 6. For every iteration, the functional values are obtained here. Here the functional value is 0 as it's the root of the given equation. The corresponding graph of the function is here. Then after finding minima, using the Newton's method we can find minima after the in Newton's method for finding minima. Similar to that, it starts with an initial guess for the minima and then it improves its guess until the desired level of accuracy is achieved. Here the formula for Newton's method is xn plus 1 is equals to xn minus f dash of xn by f double dash of xn. Here we are dealing with the single derivative and double derivatives of a function. This is obtained from the Taylor series where the notations are same and f double dash of xn represents its double derivative. And the problem here is when the double derivative calculation is hard or it obtains as 0. Then the alternative for this is using its secant method. And for in the case of multivariables, the formula for Newton's method is k plus 1 guess is equals to k minus its Jacobian into functional value. And Jacobian of a function is defined as df by dx as this matrix. And the code for the Newton's method to find minima is importing SymPy library for finding derivative and declaring x as a symbol, and Matplotlib to plot the graph. And a functional value I chose here was the same from the previous one. df is its functional value and d2 of its double derivative. Z is the input for the initial guess and n gives the number of iterations. Choosing for loop, we can choosing for loop with the condition with number of iterations. A is chosen as its functional value by substituting the value initial guess and then improving the z value by Newton's method formula, and b is its double derivative, and we obtain y as z minus a by b. This represents that k plus 1 guess is equals to k minus f dash of x by f double dash of x and finding its functional value at every next iteration and comparing them. And for plotting the graph, the interval I chose was in between 10 and appending these values into the empty list. And plotting the graph between these both points gave the result as shown. The initial guess for the root was 5 and the number of iterations I chose was 3. The corresponding values are obtained, and the graph of the given function is, the graph of the function remains same in 3 cases. The function graph same, but the concept that changes finding minima and finding a root of the given function value. And coming to the advantages of a Newton's iterative optimization, it converges fast. In most cases, we obtain root in less number of steps, and for this process only one guess initially is required. Formulation of this method is simple as the basic formula is easy to program. And the trade-offs of Newton's iterative optimization: in some cases convergence is not guaranteed. For a given equation, the chosen guess cannot get the solution. The total problem depends on an initial guess, and sometimes its derivative may be 0 and its double derivative may be 0 for finding root and minima respectively. If the function contains multiple roots, it converges slowly. In some cases, the root jumping may occur. These are the trade-offs of Newton's optimization. Coming to applications, Newton's method is widely used in optimization, image processing, circuit analysis, control systems, digital signal processing. In optimization, this is used for finding its maxima or minima by setting its derivative to 0 and solving for the root. This is useful in optimizing problems. And in image processing, in its applications such as image registration, where it is used to align 2 or more images based on their similarity. While coming to circuit analysis, Newton's method can be used to find the steady state solution of a nonlinear circuit and can be used to solve the DC operating point of transistor in amplifier circuits. In control systems, it is used to solve the optimal control inputs that result in a desired output. In digital signal processing, it's used in adaptive filtering, a technique used to estimate the parameters of the signal in real time. This method is used to minimize the error between the desired signal and the filtered signal, and many more applications can be seen in Newton's method. And the references I choose. Thank you.